Antarctica holds the world's most immense mass of frozen water, but technically speaking, it is actually a desert. Because it receives almost no precipitation, the continent is classified as hyper-arid. It also holds the record for the lowest temperature ever recorded, -89.2 degrees Celsius. And because the ice is stacked so high, it has the highest average elevation of any continent on the planet. The cold air flows down those steep elevations, creating gravity-driven katabatic winds. These winds can batter the surface at speeds up to 200 miles per hour. This diagram shows the combined land masses of the US and Mexico fitting easily inside Antarctica's 14 million square kilometers. And as it pivots to a cross-section, you can see the ice covering that area averages 1.2 miles thick. This is why humanity must operate here. Because 70% of Earth's fresh water is locked in this ice sheet, it represents the single largest variable in the global ocean system. Building a base on this continent presents a unique architectural problem. You cannot construct a normal foundation when the ground beneath you is constantly moving and the snow never melts. Take the British Antarctic Survey's Halley 6 station. It faces two constant physical threats. First, it gets buried by 1.5 meters of snow every year. Second, it sits on a floating ice shelf that slides 400 meters toward the ocean every 12 months. To survive, engineers designed a modular, segmented base. Look at this photograph. Instead of being anchored into the permafrost, the modules sit on massive hydraulic legs, and those legs end in giant steel skis. Every year, the crew uses the hydraulics to mechanically step the station up and out of the accumulating snowdrifts, and as the ice shelf inches dangerously close to the sea, bulldozers simply hook up to the skis and tow the entire research base further inland, safely away from forming chasms. Further inland, the Belgian Princess Elizabeth Station solves a different problem. Under an international mandate, researchers must minimize their environmental impact, meaning this base was required to produce zero emissions. To pull that off, engineers built a smart microgrid that harvests the continent's harsh extremes. By capturing the 24-hour sunlight of the Antarctic summer and channeling the intense katabatic winds, the entire facility runs exclusively on solar panels and wind turbines. These multi-million-dollar engineering marvels serve a strict scientific purpose. By keeping the immediate environment pristine, researchers ensure the global climate data they collect here remains entirely uncontaminated. Some of the most critical data comes from the Beyond Epica project. Their mission is to drill thousands of meters into the deep interior of the ice sheet to recover continuous climatic records from the distant past. Because the ice here rarely melts, Snell continues to compact year after year, trapping microscopic bubbles of air. The deepest layers of this ice act as a time capsule, holding pockets of Earth's atmosphere that have been sealed away for 1.5 million years. By pulling these core samples up to the surface lab, scientists can crush the ice, release those trapped air bubbles, and measure the exact concentration of carbon dioxide that was in the air at that specific point in history. This allows researchers to track something called climate lag, the natural delay between a temperature spike in one region and a reaction somewhere else. When researchers compare these deep Antarctic ice cores to samples taken globally, they find a clear chronological link between shifting polar temperatures and massive shifts in the global climate. This ancient baseline is the only way to accurately measure our current climate. By layering modern data over a 1.5 million-year record, scientists can pinpoint exactly where the natural cycle ends and our human-altered system begins. While the deep ice cores provide a static record of the past, the edges of the continent present an active, real-time threat. This photograph captures the West Antarctic ice sheet flowing outward into the dark ocean, outlining a massive, fractured boundary. This specific region includes the Thwaites Glacier. It covers a surface area roughly the size of Florida, and scientists consider it the biggest wildcard for global sea level rise. Warm ocean currents circulate underneath the ice shelf, eroding the glacier from below. This eats away at the grounding line where ice meets bedrock. Losing friction, the massive glacier slides faster toward the sea. The measurable impact is a steep upward curve. Ice flow here has doubled since 1990, accounting for 4% of annual global sea level rise. If the current trend continues over the next 2 centuries, the total collapse of Thwaites alone will raise global sea levels by 65 centimeters. More dangerously, removing thwaites could remove the structural support for the rest of the West Antarctic ice sheet, triggering a wider collapse. Surviving this environment through extreme engineering is about more than just conquest. It provides the localized, real-time data needed to forecast exactly how thwaites will impact coastal communities in the decades to come.